For this film, you'll need a notebook and pencil, and you must be ready to take readings off the screen. This evacuated glass tube can be used to study the behavior of electrons. The electrons are produced by what's called an electron gun mounted in the tube. Here's one outside its glass envelope. Let's have a closer look at it. An electric current is used to heat up an oxide cathode. Those are the connections for the current. The cathode is here, so that it gives off electrons. They emerge here at the front of the gun, having been focused and accelerated by this system of electrodes. Their velocity depends on the applied voltage. The electron beam passes through a very thin film of carbon in the form of graphite mounted on a wire grid. Let's see what happens when it's switched on inside the evacuated tube. The carbon glows red hot as the electrons pass through it. But the interesting thing is the pattern which the electrons produced when they fall on a fluorescent screen coated on the inside of the tube. It's easier to see in the dark, a pattern of rings. Now, why rings? To understand this, let's forget about electrons for a moment and have a look at an experiment using light. We'll use this ordinary slide projector as a source of light. We've made a metal slide with a pinhole drill through it, and you can see the light from the projector lamp behind. We're going to shine the light through some special diffraction gratings. The first one was made by photographing this disc, which is made up of a pattern of thousands of tiny black dots. The photograph was reduced to make this small transparency so that the whole of the disc, with all its dots, is now only about, a centimetre in diameter. When the light passes through the grating, it produces a very beautiful diffraction pattern, because of course light consists of waves and diffraction is a property of waves. The projector lamp emits light of various wavelengths. Let's see what happens if we put a red filter in front so that we've got monochromatic light. The pattern looks a bit simpler, a nice regular pattern of squares. Now we've also made a grating from this disc, which is made in two pieces with the pattern of dots in one half inclined to the pattern in the other half. Here's part of the boundary between the two halves. Once again, we've made a transparency which will act as an optical diffraction grating. This time, the diffraction pattern's a little bit more complicated. And here it is with monochromatic red light when we've put the red filter in again. Finally, we've made a much more complex grating with small pieces of the dotted pattern stuck together at random. Here's part of it in close-up. Look at the diffraction pattern this time. A system of rings. And here it is with red light. You can see the rings quite clearly. Now, this was a diffraction grating made up of many regular elements arranged at random. But the graphite film which the electrons were passing through is made up of many tiny regular crystals arranged at random. Light waves gave diffraction rings through the optical grating, so these must be diffraction rings produced by electrons behaving as waves, diffracted as they pass through the graphite film. Now, what happens if we speed up or slow down the electrons by varying the accelerating voltage applied to the electron gun? If we increase the voltage and speed up the electrons, the rings shrink. If we slow down the electrons, they expand again. To understand this, let's go back to the optical diffraction patterns. Here's the simple grating diffracting red light. Let's see what happens if we put a green filter in front of the light source. The same pattern as with red light, but there is a difference. Let's go back to the red light. You see that the pattern's the same, but that the dots are further apart with red light than with green light. Red light has the longer wavelength and the pattern's more spread out than with green light, which has a shorter wavelength. Let's try this using the grating made up of two halves with the patterns at an angle. Red light, green light. Red light, longer wavelength, pattern spread out. Green light, shorter wavelength, pattern closer together. And finally, the grating made up of a random arrangement of regular units. Red light, green light. The diameter of the rings is greater with light of a long wavelength than with green light of shorter wavelength. Changing the wavelength changes the ring diameter. So when the electron diffraction rings do this, it must be because the electron wavelength is changing. Varying the velocity of the electrons by altering the voltage alters the wavelength of the electron waves. You can now investigate the relationship between the voltage applied to the electrons and the diameter of the diffraction rings produced, and from your readings you can get a lot of information about electrons behaving as waves. First of all, we must make sure that the rings are accurately centered for measurement. By moving this magnet, we can deflect the diffracted electron beam. What you're seeing now is electrons behaving as charged particles being deflected by a magnetic field, while at the same time they are showing wave properties, producing these diffraction rings. Now they are accurately centered. We'll put this transparent scale in front so that you can measure the ring diameters. Here's the kilovolt meter to measure the applied voltage, and we'll fix the first voltage. Up it goes. You must write it down. The top scale, 3.8 kilovolts, 3,800 volts, 3.8 kilovolts. And here are the diffraction rings. You must estimate the diameters of the two outer rings. The scale's graduated in centimeters and millimeters. It's not easy because the rings are rather diffuse. You must try to judge the halfway point on the scale between the outer and inner edges of the fuzzy band. We estimate the outer ring to cross the scale at 2.8 centimeters and 7.2 centimeters. 2.8 centimeters and 7.2 centimeters. Write that down so that later you can get the ring diameter. Then have a try yourself at the next inner ring. You'll have plenty of time. Now we increase the voltage. Write this down, 5,000 volts, 5 kilovolts. And judge the positions of the two outer rings against the scale and write them down. You'll have just over a minute to do this. Remember to take the center between the two fuzzy edges of each of the two outer rings. For the last measurement, we take the voltage up further. To this, 5,360 volts, 5.36 kilovolts. Write it down. And here are the electron rings for you to measure. Again, you've over a minute to judge their position against the scale and write them down. The notes which accompany this film contain other data which you'll need and show you how to use your readings to calculate the wavelengths of the electrons at the three voltages. They also show you how, from this experiment, you can verify de Broglie's equation for the wavelength of the electron.